Hi everyone, this is our last lesson in the course. And just like our previous lesson 4.5, this is part 1. Part 2 is going to be another discussion in Microsoft Excel about how to fit data to using nonlinear regression. Okay, so we talked about it briefly in our previous Excel lesson, and I kind of showed you those differences. But in part 2 of this, we're actually going to take a set of data and graph it using, or I guess I should say, a set of data that fits well to a curve for nonlinear regression. Okay. So nonlinear regression, we saw when we did the Excel lesson that we could select other options, exponential or logarithmic or polynomial, and their trend lines were all different. Okay. So for exponential, you saw an e to the x function. For logarithmic, you saw the ln function, ln of x. And if you did polynomial, you saw the x squared term start to kind of creep in. Okay. In each of these, you still saw a function that y equaled some slope times whatever this function is. It could be e to the x plus some value. Okay. It could have been m times, we had ln of x. You still had values here for a y-intercept and for a slope. Okay, so those variables you saw in Excel are the same, right? They are a slope and they are a y-intercept, and they're found using the same formula. The only difference is that the function for x here is not just x, it's e to the x, it's ln x, or it's x squared. Those examples create a graph that instead of looking like a straight line, it has a curve. So in this instance here, okay, this curve that goes upwards like this is an example of an exponential curve, okay? In other words, the growth happens exponentially, or it starts to, the difference between previous points, okay, gets progressively larger, okay? So this difference in y coordinates, you can see, gets progressively larger, okay? That's, by definition, an exponential function. So to show you that how these work, remember for linear regression, they followed a straight line. We had this familiar formula, y equals mx plus b. Nonlinear regression simply means it does not follow a straight line. Okay, period. That's the easiest way that I can describe it. Now, we still use this equation, y equals mx plus b. But remember, when we talked about the examples in Excel, they had e to the x, or ln of x, or x squared, or x cubed, in place of just x here, okay? So to find these equations, instead of x, we write f at x, where f at x is an equation, okay? It could be x squared. I've got some examples here. It could be ln of x. It could be x squared. 1 over x as an example. 1 over x, you would see the graph would kind of go downward and decrease as you go instead of increase. Root of x. All these are examples of what f at x could be. Okay? Everything else remains the same. Okay? M is still the slope. B is still the y-intercept. M increases or decreases. Okay? We still call it a slope, but M affects, how quickly the exponential function grows or how quickly it declines. In the example of, let's say, 1 over x, where it might be, a function that decreases as x increases. Okay? So to go over these formulas, the formulas for slope and y-intercept remain the same, okay? But there's one key difference here, okay? The slope is still the number of data points n times the sum of the x times y terms minus the sum of x times the sum of y divided by the number of data points n times the sum of x squared minus the sum of the x terms all squared. The difference here is that instead of x, you're substituting in whatever your f of x function is, okay? So for instance, if f of x is x squared, then your sum of xy term, for instance, would become the sum of, instead of x, we have x squared times y, okay? Because you were not graphing a straight line, so it's not just x there, it's whatever that function is, okay? So I write the formulas the same, I just want you to understand that you have to substitute in whatever your f of x function is for each value here of x, okay? So for instance here, our sum of x becomes the sum of x squared terms, right? Because our x term is actually x squared in the equation. For our sum of x squared, okay, we have to substitute in x squared and then square that. Okay, remember our rules of exponents. So that becomes, you can either write it as the sum of x to the fourth, or you could take each term and square it. Okay, remember we have a table. So the same thing happens for our function b, our y-intercept. It does not change, just that you have to substitute in whatever f of x is. Okay, so I've noted this here, and it's very important that you take that into consideration. Okay, so we're going to do one example. I'm only doing one in this, and you're going to see why. When you get to these types of functions, especially exponential ones or ones that grow at a square or cube, the numbers get so large that it's very cumbersome and it's not practical to do it as a hand calculation, which is why, the second half of our lesson will show you how to do it in Excel. Okay. Before we do that, I want to show you just one other example of f of x so you really understand it. So let's say f of x, I'll do it in a different color. If f of x was 1 over x instead of x, then our sum of x times y terms, instead of x, we place f of x. So it becomes the sum of 1 over x times y. Our sum of x terms becomes our sum of 1 over x terms, okay, because f of x is 1 over x. Our sum of x squared terms becomes the sum of 1 over x, all squared. Which remember, if you have a fraction squared, you square both the numerator and the denominator. So this becomes the sum of 1 over x squared terms, because 1 squared is just 1 in the numerator. So I just wanted to give you one more example to show you how to do this substitution before we go to our main example that we're going to solve. Okay, so let's look at our example. So here we're finding the curve of best fit. Your textbook, if you're looking through examples, will also call it the least squares curve. Okay? So remember when we did linear regression, they called it the least squares line. Okay, just so you're not confused if you're looking at additional examples in the textbook. Okay, so for nonlinear, it's known as the least squares curve. I like to call it the curve of best fit, just that best fits the data. That's what I like to refer to it as. So find the curve of best fit for the following data if f of x is equal to v cubed. Okay. So we have velocity in kilometers per hour, and we have power p in watts. Okay. So this velocity would be our x term, and our power would be y. Okay. So remember, we have that y is equal to m times f of x plus b. And we know that our y term is power, and f of x is our velocity cubed. So we can substitute that in, and we get power is equal to m times v cubed for f of x plus b. Okay? So what we need to do here is I place the same table, because remember, we need these four variables, the sum of x, the sum of y, the sum of x times y, and the sum of x squared. But remember, it isn't just x here. So we need to replace these column headings with the proper variables. So x, instead of x, we put f at x. So we can cross that out and write v cubed, because that is our f at x function. Instead of y, I will use the term we're using here, which is power. So I'll replace y with p. For x times y, okay, x is v cubed, and y is p. So this becomes v cubed, or velocity cubed, times p. And instead of x squared, we have f at x, v cubed, and that's all squared. Okay, you can also write that as v to the exponent 6 if you choose to. Okay, it's up to you. So knowing this, I'm going to write each of our data points. Okay, so for our first column, which is v cubed, we have to take each of our pieces of data, because remember, this is just velocity, and we have to find the cube of it. Okay, so in other terms, for our first one, we have 10 cubed, okay, which in this case is equal to 1,000. For the second one, we'd have 15 cubed, which is equal to 3,375. Then following our trends, 20 cubed, 25 cubed, 30 cubed, and 40 cubed. Okay, so simplifying those, okay, 20 cubed is 8,000. 25 cubed is 15,625. 30 cubed is 27,000. And 40 cubed is 64,000. Okay, so you can see right away how large these numbers are. Okay, and that trend's going to continue. These last two columns, you can see I've made them much wider. It's because the numbers are going to get very large. And this is a major reason why this is nice to understand how to do it manually, but for practical purposes, you would do it in something like Microsoft Excel. So the y column, power p, it's just p, right? So we can take the data exactly as it sits here, okay? So we have 75, 250, 600, 1200, 2100, and 4800. Now our next column is multiplying the first two columns together. So we have, for the first entry, 1,000 times 75, which is 75,000. Then 3,375 times 250, which gives us 843,750. And continuing this trend, 8,000 times 600, which is 4.8 million. Then 15,625 times 1,200, which is 18,750,000. Then 27,000 times 2,100, 56,700,000. And 64,000 times 4,800, which is 307,200,000. So you can see, like, look at the size of these numbers, right? Putting these in our calculators alone, when we get to doing the slope and the y-intercept, take enough, right? So that's why as we progress further, you can see the next term gets even larger. Why it's done in Excel. So our next one is the v cubed term squared. So it's our first column here, each value squared. So for the first, we have 1,000 squared, which is simply a million. Then we have 3,375 squared, which is 11,390,625. Then we have 8,000 squared, which is 64 million. Then 15,625 squared, which is 244,140,625. Then 27,000 squared, which is 729 million. Then 64,000 squared, which actually gets us into the 4 billion range. 4 billion, 96 million, 96 million, I should say. Now we have to add all these up, okay? So adding up the first column, we get 119,000. Adding up the second column, we get 9,025. Adding up the third column, we get 388 million. 300, whoops, that's the wrong number. 368,750. And for our final column, we get 5,145,531,250. Okay, so we'll write sum here. So just massive numbers. Okay, so with that, we now have to find our slope and our y-intercept. Okay, our last data point that we're going to need is our total number of data points, which in this case, counting them, 1, 2, 3, 4, 5, and 6 data points. So that means that n is equal to 6. So our slope, m, is equal to the number of data points times the sum of x times y, which x times y here is v cubed times p, minus the sum of the x terms, which is the sum of v cubed, because remember, that's our first column, times the sum of our y terms, which is the sum of our powers p. And that's all divided by the number of data points times the sum of x squared, which in this case is v cubed, all squared, minus the sum of all of our x terms, which instead of x, it's v cubed, and that is all squared. Okay? Substituting in these values, we get 6 times 388,368,750 minus the sum of our x terms, which is 119,000, times the sum of our p terms, which is 9,025. And this is all divided by 6, the number of data points, times the sum of our what's called x squared, which is our last column here, which is 5,145,531,250, minus the sum of our x, which is v cubed, okay, so 119,000 squared. If you calculate that out correctly, you will get 0.075 for our slope. Okay? So these numbers look large, they actually come out to a reasonable number. Okay? The same thing will happen for our y-intercept b. Okay? So our y-intercept is the sum of our x squared, which remember is v cubed, all squared, just replacing them, times the sum of our y, okay, which is the sum, whoops, that's a terrible sum, which is the sum of our p terms, minus the sum of x times y, which in this case was v cubed times p, times the sum of our x terms, which is the sum of v cubed. And that's all divided by the same denominator as we had for our slope. Okay? Our number of data points, n, times the sum of the x squared, which was v cubed, remember, squared, that's our last column, minus the sum of our x terms, which is the sum of v cubed, all squared. Okay? Substituting in these values, b is equal to our first term, which is the sum of our last column here, 5,145,531,250 times the sum of our P terms, which is 9,025, minus our sum of our XY, which is our third column here, 388,368,750 times the sum of our first column, which was our X terms, okay, or V cubed, which is 119,000. And that's all divided by the same denominator, if you remember. So number of data points, which is 6, times the sum of our X squared, which remember was our V cubed term, all squared, which is 5,145,531,250, minus the sum of our X term, which you remember is our first column, or B cubed, 119,000 squared. And if you calculate this out, you get simply 13.3, okay? But again, you can see, look at the size of these equations with all these numbers, right? It's just not practical to do it by hand, okay? Calculating this out, remember our equation was P equals M times V cubed plus B. Substituting it in, we get P is equal to 0.075 times V cubed plus 13.3. Okay, so that's just substituting in to find our, I'm calling curve of best fit. Okay, so like I said, I only did the one example that you saw there, and this is the end of part 1, but this is our final lesson for this course. Okay, these are what I exercise, or what I recommend you try for exercises. The data is given. If you do have questions on them, please send me an email. Or send me a message on Teams, and make sure to check out part 2 in Microsoft Excel. So thanks, everybody.